Blip, blip, blip.
Okay, this video looks at exam questions which are based on practical procedures that you may have seen in the lab. These are all from the June 2013 paper, and the first question we're going to look at is a question involving mixing vinegar with baking soda. Okay, now vinegar is obviously an acid, okay, and baking soda is actually an alkali or a base. So immediately you should be thinking about what type of reaction that is. Now, what the student has done in this experiment is they've measured the temperature of the mixture as baking soda has been added. And they've plotted a graph here, and you can see it's a lovely smooth curve. And the first question on the exam is, how do you know it's not complete? So how does the graph support this statement? And you can see that the graph is still going down, it hasn't plateaued. So if the reaction had finished, it would hopefully have plateaued, the temperature would have stopped decreasing. So the answer to that question is the curve is still falling. Now, this reaction, unlike most reactions you do in the lab, was actually done in a polystyrene cup. So why is a polystyrene cup used rather than a glass beaker? And it's because polystyrene is a good insulator. So it prevents any heat change from, well, external conditions. It prevents heat loss. So, question C points out that vinegar contains an acid, okay, and it tells you the active ingredient in baking soda is sodium hydrogen carbonate. And they've actually given you an equation for this reaction. What would you see in this reaction? One observation. Now, hopefully you've spotted that carbon dioxide is produced. And what a lot of students will write here is they'll say, you'll see carbon dioxide being produced. Well, you can't actually see carbon dioxide, but what you would see in this experiment is bubbles. And the gas would be colourless, so bubbles of colourless would be your answer there. So, they then tell you that this is an acid and that one of the products, which is something called sodium ethanoate, is a salt. Describe two reactions that are occurring. Well, as we know, you've got an acid, and hopefully you've spotted you've got baking soda in there. You should already have realised that this is a neutralisation reaction. Now, the other type of reaction refers to temperature going down. The solution is getting colder, and that means it's an endothermic reaction, as heat energy is being absorbed and converted into chemical energy. Now the question continues. So here's all the prior information on the left, and here are the following questions. Now, D part 1, okay, asks you to draw an energy level diagram. And an energy level diagram shows you the amount of chemical energy in the system. So as the system is absorbing thermal energy, hence the surroundings are getting colder, the level of chemical energy in there must go up. It's an endothermic reaction. So what we're looking for here is a line above the reactants, and we label it with the specific products that are given to us in the equation on the first page. So those are our products, and that's all you need for that. Label your diagram. Well, delta H, hopefully you know that that's the enthalpy change, and the distance from there to the top, to the product, is delta H. Now, E part 1 is a slightly harsh question. Strictly speaking, this equation isn't actually on the syllabus, but as they've given you the equation and they've given you all this data, really it's about plugging numbers in. So you can read that the volume of vinegar used is 100. They've told you to use 4.2, and then you have to work out the temperature change, which is the difference between 18.7 and 13.2. And if you work that out, the difference is 5.5. So the heat energy change, if you work that out on your calculator, comes to 2,310 joules. Now, if you wanted to calculate the amount of moles in ethanoic acid, apart from the volume of vinegar, what else would you need to know? Now, for a solution, you should be thinking of using the equation that we've used all the way through the course, with moles on the top, concentration and volume. And if they ask you, apart from the volume, what else do you need to know to work out the moles? Well, you need to work out you need to know the concentration of vinegar. The second question from that paper, which I'd like to go through, is another experiment producing gas. Okay, again, it produces carbon dioxide, so you're going to see bubbles of colourless gas being produced where the reaction takes place. In this equation, in this reaction, we're looking at how the concentration of hydrochloric acid affects the rate of reaction. Make sure in these questions that you read all the information carefully, and this is about how a student has designed an experiment and what you would do in designing. So this is about keeping certain variables constant. They've kept the amount of calcium carbonate constant by using the same number of marble chips. What other properties of the marble chip should be the same? Well, just simply counting the chips isn't a particularly effective method. What you really should keep the same is the mass of the chips and the size of the chips, okay, or the surface area of the chips, because small chips or powder reacts much quicker than large chips or chunky chips, if you like. Right, this is quite a tricky question because they've given you 5 students and they've asked you to identify pieces of information that each student failed to record. So read through students 2 to 5 and then identify what they haven't done correct. Okay, so student number 2 hasn't recorded the time. Student number 3, the marble chips and 60% hydrochloric acid formed 100 centimetre cubed of gas in 70 seconds. In this case, they're missing some information about the marble chips. We don't know the number of chips used. And by this stage, it should be slightly easier. I think by the time you get here, you can see the trend. So someone's used 40% hydrochloric acid and 6 marble chips, took 105 seconds to collect the gas. We don't know how much gas. So volume of gas. And the final one, 100 centimetre cubed of gas was collected in 135 seconds when 6 marble chips were used. In this case, we don't know the concentration of the acid. The question moves on and you're then asked to plot a graph. Note down that you're asked to draw a straight line of best fit. You're not always asked to draw a straight line of best fit. Now, I'm not going to draw the graph very accurately now, okay, because really I want to focus on other things in this video. But if you draw the graph accurately yourself, what you'll notice is the point at 20 doesn't quite fit on our straight line. So it's the point at 20 which is anomalous. Okay, the points might not be quite in the right place, but I'm doing this very quickly. Now this is a question where students tend to find this quite difficult. What you have to do here is you have to be very, very specific over the errors in the experiment that could have caused this anomalous result. And what it's important to do is realise that actually the rate of reaction is quicker than it actually should have been. So what could have caused the reaction to be quicker? Well, perhaps the concentration of the acid was too high. A higher concentration of acid would mean a faster rate of reaction. Okay? Perhaps the student used too many marble chips, okay? Or perhaps marble chips with a bigger surface area. Okay? So too many marble chips. What else might cause the reaction to be faster than it should have been? Well, perhaps there was a sudden increase in temperature at that point. So temperature too high. Now note down that I've been quite specific with the problems that are going on here. Okay, I've said the concentration of acid was too high, not that I'd just done it wrong, okay, or a mistake had been made when measuring the marble chips. I've said then there were too many of them. Okay. Now, the final question is use your graph to estimate the rate of reaction. Okay, all you need to do is read off the axes at 50% and read across, and it should come out as something like 2.4 okay, centimetres cubed per second if you've plotted it accurately, unlike myself. The final question talks about a titration, okay, where we react an alkali, sodium hydroxide here, with some sulfuric acid. And first of all, you're presented with 4 different pieces of apparatus which are used to measure volumes. Hopefully you know the names of these. This is a pipette, and that is very, very accurate, and it only measures one specific volume, in this case 25 centimetres cubed. This is a burette. It's very accurate. It's not quite as accurate as a pipette, and it can measure variable volumes of liquid. This is a beaker. It is not an accurate piece of apparatus for measuring volumes, and this is a measuring cylinder. Reasonably accurate, but not as accurate as a burette or a pipette. So, questions are down here. Give the name of the most suitable piece of apparatus in the diagram which should be used in step 1. Now, in step 1, it just says obtain about 150 centimetres cubed. These 3 pieces of apparatus are too small. You've been given the volumes. So the first piece, or the first answer, is we're going to use the beaker. That is sufficient. Okay. And in step 2, give the name of the piece of apparatus in the diagram that should be used instead of a measuring cylinder in step 2. Now step 2 says that you just want to add exactly 25, and the pipette does that exactly. So the answer here is pipette. The third question is about the choice of indicator for this reaction. Now, universal indicator is not a suitable indicator for a titration, and that's because universal indicator has a whole range of colours it turns. When you're doing a titration, you want a very specific colour change at one particular point. So phenolphthalein is an excellent indicator. When phenolphthalein is in an acidic environment, it's colourless. When the environment turns alkaline, phenolphthalein turns a lovely pink purple colour, a magenta colour, and it goes from colourless to magenta within one droplet of liquid. So it's a very, very obvious colour change. Universal indicator doesn't have an obvious colour change. It's a gradual colour change. So colour change is over a range. It's not sudden. The next question asks about the liquid sulfuric acid which is added from a burette. Why is a burette used rather than a pipette? Well, a pipette can only measure one specific volume of liquid, and we don't know how much sulfuric acid is needed to react with our sodium hydroxide solution, and a burette allows us to measure variable volumes of liquid. Okay, so the answer to this is a pipette can only measure one volume. And unsurprisingly, the next question is about actually measuring volumes in a pipette. Sorry, not in a pipette, in a burette. What you can see here is, if we have a look at the pipette, the burette reading before the experiment starts, you'll see the scale descends. So we go from 2 to 3 to 4. And the markings on here are in tenths. So we've got 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8. Now the line, the meniscus of the liquid in the burette, is between 2.7 and 2.8. So the burette reading before is 2.75. 2.7 was there, the liquid is halfway between, so it's 2.75. The final, or the second decimal place when we read a burette, is either a 5 or a 0. It's not possible to distinguish between it being 2.02, for example. Okay, it's either halfway between the lines or bang on them. Okay, so it's either a 5 or a 0. And you can see that here. We go from here 22.1, 2, 3, 4, 5, 6. Now that wouldn't score me full marks because I've got to show that I'm using the second decimal place, which is either a 0 or a 5. Now as the meniscus in this case is exactly on the line, it'll be a 0. And when we take those numbers away from each other, 19.85. Do be careful, because it's a little bit awkwardly set out that in this case the first number that you require in your table actually comes from the burette here. So just be careful when reading the questions. Now if you've done sufficient practice of this, you should know that you'll be expecting some kind of calculation coming up. Before we do the calculation, they actually report the results which were recorded in this experiment, and they ask us to identify concordant results. Now concordant means results which agree with each other. So we have to look for results which are within 0.10 of each other, maybe within 0.20 of each other, and these two are very close together. You can see that this is a little bit further away. This is 0.25 away from that one, which is a little bit far. So we're going to just pick those two results, and that enables us to then take an average volume. And we can work that out as 23.40. The question, and indeed this video, finishes with a moles calculation. Again, using solutions. So you will need your triangle with moles at the top, concentration, and then volume on the bottom. And rather than just getting you to work it out, they've given you a sample calculation in 3 steps. They've worked out the number of moles, they've used the mole ratio, and then they've worked out the concentration. But in each step, there is a mistake, and you've got to spot the mistake. So, the mistake in step 1. Well, what they've got here is, well, this number here is the concentration. Is that the correct concentration of sulfuric acid? You might need to go back to the previous slide to check it out. It is. is that the correct volume of sulfuric acid? Well, the volume's up here, as is the concentration. Yes, that's right. Now, they've divided by 100. That's the mistake. What the candidate or the person should have done was actually dividing it by 1,000. And the reason they divide by 1,000 is because you're converting your centimetres cubed into decimeters cubed. And they've made a mistake here by dividing by 100. So that gives the person the moles of sulfuric acid. Now in the next step, the student has correctly decided to work out the moles of potassium hydroxide. And to do that, you need the mole ratio. So if we look at the mole ratio here, if I had 1 mole of sulfuric acid, I'd react that with 2 moles of potassium hydroxide. So we don't have 1 mole, we have this many moles. So we'd expect to double it to get our moles of potassium hydroxide. The candidate hasn't doubled it, they've divided it by 2. So in step 2, you need to times by 2, not divide by 2. Which brings us on to the final stage, possibly the most difficult bit of this question. They're working out now the concentration of potassium hydroxide. And if you use your triangle, you can see that concentration is moles divided by volume. And that's what this candidate has done. They've got the moles, which they worked out earlier, so that's in the right place, and they've divided it by volume. But that should be the volume of potassium hydroxide. The volume of potassium hydroxide used is 25, not 23.60. So the mistake is that it should be divide it by 25. Most candidates probably will go for the 1,000 as the mistake. And actually, that's not the mistake, because the timesing it by 1,000 is what you're effectively doing when you convert this number here into decimeters cubed by dividing it by 1,000. So the mistake is that we should be dividing it by 25 rather than 23.60. And that's the end of this video.